Thank you. It's really exciting to be here. It's my actually first in-person conference in like 3 years. So pretty excited to talk about this topic, detecting silent detecting silent errors in the wild. So what is a silent error, right? So the error that I've put on the screen is an example of a silent error because it just computes an incorrect value. There is no log in the system which tells you that this miscomputation has happened. There is no system event, there is no machine crash. So what ends up happening is this computation gets propagated to numerous applications within a large infrastructure. And these applications consume these miscomputations and make incorrect decisions which affect end users. So just to highlight the scale at Meta, right? We have 3.6 billion monthly active people. So this means billions of requests every second. And this also means millions of CPUs. So when I have data corruptions which are occurring on at that rate of 1 in 100 or 1 in 1,000, we end up facing significant challenges at an application level. So I'll talk more about what is the scale we see these data corruptions at, what type of defects that I'm talking about, and why is this not a solved problem, and stuff like that. So, right, silent errors, and very specifically I'm talking about data corruption within the CPUs. So these are CPUs that you would buy off the market, Intel, AMD. So these are defects in silicon. They are hard to detect, and what we've observed is that these corruptions can go undetected for months or years, and the application continues to consume these corruptions without a user knowing about it. And we have seen significant impact to services. If you're familiar with site event terminologies, this more often than not, every single CPU ends up in a SEV1 scenario for our fleet. But you might say that this is a solved problem. We have seen this before. Cosmic rays, they cause bit flips. We've also had in the 90s a Pentium FDiv, where it was a special function which just did incorrect results. So isn't this a solved problem? So what I want to drive contrast towards here is cosmic ray induced faults typically occur at one fault in a million devices. So an equivalent odd for that is an earthquake in Seattle in the next 5 to 6 hours. That's actually a very rare event. But what we are talking about here in terms of silent data corruptions within our fleet is one fault within 1,000 devices. This is actually significantly larger than what we have thought these corruptions to occur at. And the odds, I've chosen a very special example here, but the Golden State Warriors were tipped to win the NBA Finals at 0.1%. It did end up happening, but this is a lot more commonplace than one fault in a million devices. So to explain the severity of this problem, I want to walk you through an example case study. This is a real SEV that happened within our fleet. So here we are doing a map reduce type of operation, and we are trying to do a decompression of files, and we are in the reduce stage, shuffle and merge stage rather. And what we have here is a bunch of files which are compressed within a Spark database. So what we're trying to do here is we are computing file size for decompression, and when we are trying to decompress, do that computation. So this is an Apache Spark architecture, so we are using Scala for the computations. So the Scala math.pow function is invoked. So when typically compressed files are stored as chunks, and you multiply the chunks by the number of a power function, and then you identify where you need to put that chunks data at different points in a file. So we invoke this power function. It so happened that this landed on a defective CPU, and we were supposed to compute 1.1 times 53, but we ended up computing an incorrect result here. So what it meant was we had a check at the end of it, which was checking if the file size is greater than 0 or not. And if it evaluated to 0, we just skip writing that file. So what this meant was we had files which actually had valid data, which when we decompressed, the files were missing. So this led to a number of holes within the decompression pipeline, and this kept happening for a month, and we couldn't figure out. So actually software engineering team spent 1 month trying to identify which machine was the root cause within a cluster which had this corruption. So as an end user, when you're presented with this problem, you just see random holes that are appearing in your decompression pipeline. But when we started root causing this, we identified that it was actually one CPU on one core for one instruction for a particular set of data values, which created this problem. Now imagine millions of CPUs across a large infrastructure. So I'll walk through how we debug this and the timelines around it. So this software side effect is appearing for 1 month. And now I'll walk you through the process of how the entire debugging process worked. So we have Spark workload, which is in Scala. What we have here is an occasional reproduction of the issue. So every now and then your workload would randomly get scheduled on that machine. It would just so happen that there's data values which are aligned for that defect which is there on that CPU, and you would just hit this defect. So what we did was it was a single core workload. We multi-threaded it, and on that machine that was identified by our software partners, we found that it was 100% reproducible on core 59. But it is a Scala workload, so I can't really see the assembly that it is executing on the machine. It's just too high a level language for me to decompress. And actually Scala doesn't also provide you with any tools to actually understand the assembly that it executes. So what we did was we re-implemented the Scala functionality within Java while also maintaining the ability to reproduce the defect. So again, now you have Java bytecode, and we have core 59 of the reproduction. So Java, I think everyone here knows, it's just in a compiled language. So it also doesn't provide you what assembly it executes ahead of time. There was actually a tool which is called GCJ, which attempted to do that, but it was deprecated in 2008. So we didn't have a way to identify, okay, what is happening in the CPU level. So what we did was we actually let the code run. We used the VM hotspot profiler. We had this profiler enabled within the fleet. So the code executed, and then we extracted all the assembly that it printed as part of the profiling. So now we ended up with 430,000 lines of assembly code. So once we started parsing the relevant functions, we reduced that 430,000 lines to 400 lines of assembly code. And finally, we started reverse engineering exactly what this Scala function did. So we were able to identify the equation that it uses when you're doing a power computation. This is a smarter way to do the algorithmic optimizations. There's an optimization for square, and it allows you to just compute faster if you use this formula over traditional other methods. So what we were able to do here was reduce this to a 60-line assembly. And this 60-line assembly, we integrated it into our fleet scanning mechanisms and rolled it out to the entire fleet. And what we found out is not just one machine. We hit more than 100, 120 machines, which had the exact same defect for the exact same family of errors. So this is an example of one defect, one CPU, one core, one instruction causing havoc within a large-scale application. And I'm here giving an example for one family, but this is something that we observe at 1 in 1,000 devices. So it's a routine practice for us to go through these kind of effects, identify minimal reproducers, and then scale it out to the fleet. So I also want to talk about why this is a hard problem within a large fleet, and give you some observations of some samples that we have seen within our infrastructure. So the first one is data randomization. So whatever defect I discover, I described previously, if you just change the power from 1.1 to the 53 to 252, it would work. So there is a very specific data points that you have to provide for you to hit the defect. There are also electrical variations. For example, we played around with all these defective parts, and we were able to identify that the device does not give the same result at different voltages, different currents, different frequencies. And there are also environmental variations, right? So as soon as we started playing around with the temperature of these defective devices, we found that it's not always giving you the accurate result at every temperature value. And there's also some seasonality that we observe within different data centers, where some data centers are more prone to this as compared to other data centers. And finally, life cycle variations, right? So if I test a device today, there is no guarantee that I have the same accuracy for computations tomorrow. So this was actually a very specific experiment that we did, where we took a device, ran the exact same computation on it for 6 months. After 6 months, it failed for the exact same computation it has been running for the past 6 months. So this forces us to continuously test within a fleet. So just because of the nature of the defects that we are observing, we have to come up with frameworks which allow us to periodically test, as well as test within a live production environment. And that's what we have built to support, to mitigate the effects of this within our fleet. So I'm going to talk about 2 different frameworks: Fleet Scanner, which stands for which is a way for us to do out of production testing, and a second flow which is called ripple, which actually sits along with the workloads and then allows you to test the devices for data corruptions. And this is actually in addition to the tests that we do at our manufacturer as well as at DC Intech. So every time we put a rack within a data center, we actually put it to like rigorous testing. But in spite of that, just because of the nature of defects around life cycle and temperature variations, we have to continuously test within the fleet. So I'll walk through these two flows. So the first one is fleet scanner. I've created sort of a state machine animation here for you to visualize what happens within a live fleet if there's like a server going through this flow. So there's a server in production, and what we do is, we do my workload migration and the server is drained. And more often than not, this server draining happens because you're doing firmware upgrades, provisioning, a repair, a kernel upgrade. So you're basically piggybacking on maintenance flows, and we execute out of production testing. If the server fails, or if it fails for any of these test reproducers that we have written, we put the server in a quarantine pool, and then we run a lot of experiments on it to identify, how quickly we can time to failure, or the ability to detect many similar defects of similar families. And once we establish a good confidence around it, have a good reproducer around it, which we can scale through the entire fleet, we put it through a different flow where we say it's now a high confidence signal, and we move that server to repair. Once the server is repaired, we do a verification process. The server is undrained after verification succeeds, the workload is migrated back, and the server returns back to production. So what happens within this out of production testing, right? So this is the schema for the fleet scanner mechanism. So there's a test repository where we keep updating with different assembly level tests, C level tests, C++ level tests. And then we put in a different granular controls. You can control which maintenances you want to piggyback on, which tests are allowed for which maintenances, and what are the total time durations that are allowed in each of these phases. So then eventually, based on this kind of information, the tests are generated. The machines go through these kind of out of production testing. There are statistical models which feed into results from past tests as part of the new generation mechanisms. And finally, we also aggregate every test that has been run in the past 3 to 4 years into a result database. So the retention is significantly long so that we can draw long-term correlations. So to summarize, here we are kind of taking pit stops to run tests within a live infrastructure. We run it in non-production states. There are directed tests which are run. And the testing time is usually in the order of minutes within these flows. And we are able to achieve the entire fleet's coverage within 6 months using this flow. This is an artifact of fleet size, how often you test, how often you upgrade kernels, how often you upgrade firmware on your devices. And we have detected more than hundreds of devices. So as part of lifetime of this tool, we've been able to test for approximately 4 billion test fleet seconds. But this is still too slow across a live fleet. If I have a new defect today, I cannot really wait for 6 months to be able to clear my fleet to say, okay, that defect doesn't exist within a fleet. So what we came up with was a different flow, which sits actually with the workloads. So this is co-locating with the workloads. This is sort of a special workloads, which runs a dedicated set of instruction which has millisecond level footprint. So these are time sliced and dynamically controlled in production instances. So think of this as a service which is actually going and hunting bit flips across the entire fleet, but it has extremely low footprint so that the application performance is not affected. And the flow that we follow every time we detect a failure is very similar. Server is in quarantine pool. If it's low confidence, it goes through experimentation, multiple iterations, and then we up-level the signal to high confidence repair, and the server is undrained after a repair execution. And what's different in comparison to fleet scanner here is there's actually a very specialized scheduler with fine-grained control. So this actually has the ability to identify which workloads can I co-locate with. Should I run for 100 milliseconds or 10 milliseconds? Should I run every 30 minutes, every 60 minutes? So there's a way to dynamically control all of this based on which workload type and what is the pressure that is seen on the machine. So this feeds into this ripple test controller. And the ripple test repository is also a very specialized set of tests, which are just a sequence of assembly instructions which do not create a large enough footprint on the machine that is running the workload. And similar to last time, we put all of these results into a long-term analytics database, and we try to understand what's happening with all these defects. So to summarize, workload collocation in production tiny tests. The tests are in the order of milliseconds. And the time to fleet coverage here is 15 days. So this is what we get as a benefit of this. We cannot run tests for long, long duration in minutes, but we are able to obtain coverage for a new defect within 15 days if it's too targeted. And both methods of testing provide unique coverage. So what do I mean by that, right? So if you just compare the two different mechanisms here, so this data that I'm sharing is from 3 years of infrastructure testing for the entire Facebook fleet or Meta fleet. Yeah, it's actually for like one very large defect family. There are multiple defect families which we categorize based on whether it is vector type, memory copy type, floating point type, and this is for like one of the largest defect families that we've seen issues for. So one of them is performance aware. For example, Fleet Scanner is not performance aware, Ripple is performance aware, and the time to equivalent coverage is approximately 6 months for one and 15 days for the other. So this is like sort of a Venn diagram of how these coverages intersect. 70% is something that both these mechanisms are able to achieve. So in 15 days, I'm able to like get to 70% of the coverage. There's a 7% coverage which is unique to Ripple, which just comes from like being able to co-locate with the workloads. So that allows for instructions heterogeneity for you to be able to like detect a different type of corruption. And there is 23% which are just, these are defects which you can only hit if you run the tests long enough and create that kind of electrical condition. So I also want to give you some interesting observations around this. Like it's not just that first example that I showed. There are like scenarios where the number is just incorrect, right? It's not just always zeroed out. And there are scenarios where the number is supposed to be 0, but it's non-zero. And what we have observed is that these errors tend to be compiler and optimization dependent. So the issue that I described as part of the case study, if you wrote the same code in C++ or C, that you would never hit it. You had to write it in Scala. You had to write it with that appropriate optimization. And we found that even the assembly reproducer that we wrote, if we change the optimization level from O3 to O2, the assembly reproducer as well as like the C structure around it, it wouldn't hit the defect. So you have to create that special condition within the machine for you to be able to detect this. This, as I mentioned, this also impacts computations involving non-zero operands and results. And it also affects varying degrees of precision. So we have seen in the 4th decimal point, or sometimes it's just the direct number itself which is incorrect. And this is something that we are seriously worried about because it affects multiple instruction types, numerous types of workloads. So we have seen vector instruction types affected, floating points affected, large data moves affected. So if you're just copying files, you're thinking, hey, I'm not doing any computations here, but actually the copy libraries still use advanced vectors behind the compilation. So yeah, you end up just copying files and the data doesn't match from the source to destination. It affects gather scatter operation. It affects encryption. We've seen the numerous encryption architectures fail, and we are just locked out of certain machines just because the encryption of that machine just happened to land on a CPU which had defects. We've seen shared memory coherency deadlocks, and we've also seen string corruptions across our Presto databases. So as I mentioned, it also affects cold storage applications, backups, Presto queries, kernel code. So the takeaway here is we are saying that it is one defect per 1,000 devices, but what we really don't know is what percentage are the unknown unknowns, because all we can detect is at this rate, one defect per 1,000. There are still so many reproducers, so many assembly level stuff, which could be happening in the fleet, which we have no idea, what percentage they are. So that's what we are trying to solve using 3 different approaches. One is hardware design strategies. We are working with manufacturers across the world to come up with fault-tolerant designs, put a lot more priority on data protection and architecture, which actually puts a lot more value in ECC and fault protection logic. We are also doing specialized screening at all these manufacturers. So every time a CPU or a component is manufactured, it goes through a specialized screening at their facilities before it gets shipped to us. And we are also looking at scale collaboration. There is no way a manufacturer would have the same scale as we do. So what we are trying to help the community with is by providing as much data as possible around these DPPMs, defect types, defect families, and get the community to think about ways to mitigate this in design, in architecture, and also in silicon technologies. So that is at the hardware design side. In the production fleet, as I think this is probably the core of the talk, is we are doing manufacturing validation, we are doing out of production testing, we are doing in production testing, and we are constantly evaluating what it means to operate within those thresholds, pay those costs. Because ideally, I don't want to test CPUs, but we have to do it because of the defects that we're observing. And finally, we are also exploring, and we've implemented a bunch of these within our fleet, which are software and application strategies. So we've implemented a bunch of libraries within PyTorch with algorithmic fault tolerance. there are a number of services which actually run with probabilistic redundancy within our fleet. So that means 1 to 1.5%, like 1 to 2% of the workloads randomly get executed on 3 different machines, and they do an ensemble comparison to validate that the computations are same like every now and then. And finally, we're also doing something called a software fault correlation. So every time an application crashes, what is the signature that I should look out for to identify if it is actually like a CPU defect versus it's a software engineer's mistake. So that's actually a very hard problem. We are trying to invest and work with our kernel partners as well as like software partners in enabling that. So what we are observing is with increased silicon density and technology scaling, we are more likely to see these corruptions in the future with CPUs and ASICs. And we need to build monitoring and detection solutions as a community to make sure that this is up-leveled enough for our CPU vendors to take care of it. So this is my final thought, right? It's a silent errors are like a foundational computing problem that we are dealing with just because of the silicon technology scales we are at, as well as the reliability practices we have followed in the past decade. So we as a community need to do a lot more, come together, hardware, software, kernel community, and work towards solving this problem. Thank you.
We got a few minutes for some questions. Anyone have any questions? And then just for the streamers, thank you for letting us know in the stream. If you could just repeat the question when it comes in. So yeah, any questions? Got a few minutes.
So the question is, you mentioned bit flips. Have you considered using ECC, Reed-Solomon encoding, or some kind of a check before and after an application executes computations? So the devices within a server, if you look at memory, they all come. Within an enterprise application, we typically use ECC DDRs. So memory is not the source of these corruptions, and even for disks as well as storage devices, there's a bunch of encoding as well as checksum validation that happens before the data gets written into these storage devices. So what we've identified is majority of the corruptions are actually because there are too many unprotected paths within the CPU where the ECC is not implemented at all. So there are blocks which just there is no protection, and there is no parity protection, there is no ECC protection, so there is no way for us to know what percentage that is. It's a trade secret with our CPU vendors, but that's where these corruptions are coming from. Sure.
When you actually identify these assembly level issues, right? I'm actually curious, if you documented the procedure for if there are anything I can read on how you actually narrowed it down to an instruction that 60 lines of assembly. Is there something we can read to learn more about it?
Sure. So the majority of the content that I presented today is published as 2 papers. The first paper is mitigating or silent data corruptions at scale, and the second paper is detecting silent errors in the wild, which is exactly the name of the talk. We do plan to someday release the exact 60 lines of assembly. I think it is almost out in the open, right? Google published a follow-up paper to our paper, and they mentioned the instruction which failed. So I guess we now have permission to release it. So I want to do it. We are working towards making it happen. So the question is, do you think these are fact of life, or we should get used to them, or is there anything that the manufacturers can do to mitigate them? So there are choices which are being made, which have been made in the past decade to provide a lot more features into our CPUs without actually accounting for reliability. I think it's about true with the type of transistors we use, it's about the type of testing we use. For example, as soon as you talk about any CPU that enables AI or ML, you're adding a bunch of bits which support fast matrix multiply. As soon as you do that, if you don't have the cost accounted for reliability of those blocks, it becomes a prone block for these data corruptions. So I think one way to look at this is to take a step back and look at all the features that we've enabled and start looking at which blocks need a lot more of these ECC type of protections. But at the same time, I think we won't, I mean, we will never get to a stage where it is 0 faults per million or any of that. I think that this will stay with us. What we can attempt to do is continuously reduce them by using like, testing mechanisms or by making conscious design choices. And the silicon development cycle also tends to lag, right? If you make a decision today, we'll probably see that implemented in 2027, right? So there is that delay in communication and, in just the implementation cycles. Yes.
Do you send the faulty chips back to the manufacturer? Do they do anything with them?
So the question is, do we send the faulty chips to the manufacturer, and do they do anything with them? Yes. So we actually sent the faulty chips along with the reproducers and said, just run it, and then you will see the defect. And they actually do integrate the tests we send as part of their testing facilities, like manufacturing flows as well as production flows. In addition, they're actually, they do a deep dive failure analysis and they give a failure report back to us. And I also want to say that, it's really hard for the vendors to do this because they don't have the sequence of assembly instructions to actually hit the defects unless we provide it to them. So that's where we've been collaborating a lot. And I think Intel has open sourced a tool which is called as OpenDCDiag, which is a tool which is available, which consists of all these special reproducers that we have shared, Google has shared, bunch of community people have shared, and that is available for anyone to access as part of open source. But the short answer is yes, we get a lot of information about the failures.
Looks like one more back there. Straight back. Yeah.
Hello. I had a question that was related to the long-term trend analysis that you referred to. You mentioned that you guys do analysis on like a 3 to 4 year time range, right? What kind of analysis are y'all doing at that level of time range, and what value do you get out of that? Because things change a lot in a year, let alone 3 or 4.
True. So the question is, what value do we get out of long-term analysis, because things change a lot within a year or two. So when we deploy a product, it typically stays within our production for 3 to 4 years. So for us, there's also the production deployment cycle is also 18 months long. So let's say if I'm building a new Skylake server today, I'll continue to build them for 18 months later. So what I can gain from these long-term analysis is being able to predict if there is a need to the bathtub curve failure modeling. So let's say if there's a ramp in failures that I see at 2.5 years, I know exactly what I'm supposed to do, to mitigate them or to take these machines proactively out of production. That's one strategy. And the second reason that we do long-term analysis is to identify if there is a hotspot within the cores or within the design architecture itself. So if you look at these in a single CPU, single instance, everything seems random. But if you put more of these together and start looking at it from a long-term perspective, you can identify a lot of trends with respect to time to failure, which modules fail, which functional units fail, and at which time in the deployment cycle. So that helps us mitigate stuff in manufacturing, it helps us mitigate stuff in the fleet as a proactive measure. Yeah.
Thank you.
Awesome. Thank you very much. It was great.
Thanks a lot.